Hey folks, Dan here. Today on the MicroArch Club podcast, I am joined by Thomas Sohmers. Thomas is currently the founder and CEO of Positron AI, which recently emerged from stealth with its first product, Atlas, which is a transformer inference appliance. We talk about what makes Atlas different than traditional inference hardware and how Positron is able to deliver significantly higher performance per dollar compared to current GPU solutions. However, we start out at the beginning of Thomas's fascinating journey, which began with dropping out of high school to start a chip company at age 17. We cover his experience in the Thiel Fellowship program, why there's a need for a new instruction set architecture, and how he and a team of 3 other engineers were able to tape out and deliver a new chip in a highly compressed time frame. Thomas is an ardent student of computing history, which made this discussion a ton of fun as we connect the dots from research papers in the 70s and 80s to the cutting-edge processors of today. Before we jump in, I wanted to thank Michael, who is the co-founder and CTO at Lambda, for initially connecting Thomas and I a few months ago. With that, let's get into the conversation. All right. Hey, Thomas, welcome to the show.
Hey, thanks for having me.
Absolutely. For folks who don't have context, which I guess is everyone, Thomas and I spoke a few months back. Michael over at Lambda was nice enough to connect me with Thomas. I know y'all have worked together in the past, and I was just kind of just trying to talk to folks who had experience that I was interested in as I was kind of learning more about processor design and trying to learn more about the industry. And Thomas, you were nice enough to spend some time chatting with me. And then you have a new venture that you're working on, which I'm sure we'll talk about at some point in this show. So now is kind of a great time as you all have come out of stealth to circle back around and have you on the show.
Yeah, well, thanks again for inviting me. And always excited to be able to talk about computer architecture and computer history.
Absolutely. Well, it's interesting. I as a little behind the scenes here, I guess, I haven't released any episodes yet, so I've just been kind of doing recordings of this show. And most of the folks I've talked to worked in the industry kind of in the 70s and 80s and are now retired and are very happy to talk about their experiences. But I'm also trying to get, folks who are hands-on today and really get a sense for, what has inspired the work that's happening today, as well as what modern work in processors looks like. You have a very, very interesting background, though, that I think I'll probably not have anyone else on the show who has something similar. But you, I believe, dropped out of high school, right, after getting the Thiel Fellowship. Do you want to talk a little bit about how you got interested in computer architecture and then how that whole process came about?
Yeah. So I think some of my earliest memories, like 3-4 years old, were when I was in front of computers. So I've been a computer user and very interested in them since then. So this is right at the turn of the millennium. So back still like early memories of dial-up tones and such, but the fact that my parents let me on the internet in 2001 when I was 5,
right.
Maybe good or bad idea, not sure, but I just had it was my obsession to be playing with computers, and I started to connect like more just using it as a tool and like the interest in could play games, can actually learn things online. I was throughout elementary school very into trying to research as much as I can and just dive into Wikipedia for 3+ hours at a time. But yeah, my dad also purchased electronics kits from the 60s and 70s, the old 100 projects in one things, and so I also then got very interested in not only do computers do all these amazing things, but I can actually take a little piece of cardboard with a whole bunch of components and follow this instruction booklet, which I think I actually started using those booklets before I actually knew how to read, and can make a light turn on, and then graduate to a crystal radio, and so on and so forth. So yeah, it was really those really early formative years that got me interested in electronics. Um, and then by the time, late elementary school, middle school, I just would take apart everything in the house, and thankfully had parents that were okay with me taking things apart as long as I convinced them that I could put it back together.
Right.
And I had a pretty good success rate of that. But even when I couldn't put something back together, if I showed that I actually learned something about it, then they weren't too mad. Uh, so,
That's awesome.
but yeah,
We've talked a little bit, about kind of like digging through abstraction layers, and I've heard a lot of folks who have somewhat of a similar early interest in computing who end up being software engineers, but you kind of push down, and maybe it was some of that electronic kit influence and that sort of thing. But what was it that kind of brought you from using computers to want to dig down and understand mechanically how they work?
yeah. I think those early experience with just really basic electronics kits, I really appreciated putting my hands on things, and especially experimenting, like, okay, are there other ways that I can get this to function other than what the instructions tell me? And I think it's similar. I probably unsurprisingly was loved Lego sets, but I would go buy a Lego set, put together what it said, at least maybe half of it, and then have more fun just making something entirely new. And so that hands-on aspect, I think, was just always with me. And then by the time I actually started learning, computer programming, thankfully in middle school, I was able to get into a public charter school called the Advanced Math and Science Academy, and they actually, were starting, teaching Python in sixth grade, and so I actually got much more interested when they were teaching Python, learning that. But then on the side, I had Arduinos and a few, basic stamps and stuff like that, and started more on the C side, but also learning Python. But I guess even though I learned and could appreciate and build some things on Python and higher level software side, there was nothing like it was nothing like writing C code and then getting the very simple Arduino version of C and being able to get that to run and actually blink an LED.
Right.
So it was really just always on that hardware side for me.
Gotcha. And so then you get into high school, and I assume that's when you applied to the Thiel Fellowship. How did you learn about that, and what was kind of the process for getting into that program?
Yeah, so when I was in eighth grade, so still middle school, the director of the computer science program at my high school recommended that I went to this event at the Google Cambridge office, and I grew up in central Massachusetts. So what there was a day, encouraging, middle and high school students that they should, study computers. And I was already pretty hard set on that. But there was a woman there who was, I believe, a manager, director, or something at iRobots, which is a local Boston area company. And I met her, she thought I was smart. And then a couple weeks later, she emailed me out of the blue through my school and sent a link to the announcement of the Thiel Fellowship. This was back in 2011. And
wow.
She said, she knew one of the organizers of the Thiel Fellowship, and she said that it looked like something interesting for me. The kind of crazy thing about it, I was 14 at the time, so it was a bit young for it. So at that around the same time in 2010, I started actually being a research affiliate at a research lab at MIT, and worked there for 3 years, and then finally in 2013, I got accepted into the Thiel Fellowship.
Wow, that's incredible. I mean, you obviously showed quite a lot of promise, but also really great of her to reach out. And I think a lot of times we look at folks, maybe being in eighth grade or something like that and assume, well, maybe they can do that later. But that's really cool that someone was looking out for that and thought it's never too early. So that obviously had a really positive impact.
I think the good thing was the director of our CS program at our school was. I don't think she realized that it was actually dropping out of school was the encouraged thing.
Right.
And so I'm sort of doubting that if she knew that would have made that connection.
Right.
But yeah, it was pretty serendipitous.
Absolutely. So you get into the Thiel Fellowship, and I believe there is kind of like a period of time where you're kind of figuring out what to work on, right? How long was that period of time? And then obviously you and some other folks founded Rex Computing. What was kind of like the process of getting into Thiel Fellowship and then getting to that point of starting the company?
Yeah. So the application for the Thiel Fellowship at that point closed, December 31st, 2012. So I applied then. But for basically the past year and a half, roughly before that, the main project I was working on at MIT was maintaining and doing tests on the cluster computing system at the ISN, the lab I was at. And the particular focus, I was evaluating a whole bunch of new ARM-based processors for use for cluster and high-performance computing. And we were the first to benchmark the Calxeda, if anyone remembers them, the first ARM server processor back in 2011, 2012 timeframe. So that was really my formative years learning on distributed computing and aspects really at a much higher level than the actual processor architecture, but was very interested in the idea that processors that were designed for embedded systems, ARM at the time was really just embedded and industrial and mobile, and really smartphones were really only just starting to really kick off, and ARM was getting some real steam with that. But the key thing there when applying for the Thiel Fellowship was this idea that I wanted to bring that sort of research work and my belief that, okay, these low-power processors are going to be able to actually scale out and utilize them for general, server, industrial, web server processing. And that was, I would say, a pretty risky, novel idea outside of, Calxeda at the time was basically the only company pursuing it. And so that was my Thiel Fellowship application, was utilizing and continuing that work, but actually starting a company around it. So there was a whole multi-round interview process for the fellowship, and then got selected in May of 2013 and moved out to the Bay Area in June. So basically that startup, really just getting my lay of the land in the Bay Area. I was 17, had just, moved out, never having been away from home for more than 2 weeks, and so getting to meet the other folks in the Thiel Fellowship. There's 20 selected per year, all under 20 years old, and spent basically that summer getting a lay of the land, and actually incorporated Rex in August of 2013. Okay.
Yeah, so pretty quick from the beginning. And when you incorporated, you already had kind of the idea for what you wanted to do as well?
Yeah, the idea originally was generically, go after low power, high performance computing. The target market for that was, the big data, being the big buzzword at the time.
Right.
Data centers for, the earliest folks that I was, talking with were at Facebook. So I got involved in the Open Compute project pretty early on. Later became a coordinator for the high performance computing group within OCP. Effectively the really high level outline was there. The first about 6 months after that, basically through the end of 2013, was really focused on utilizing ARM And it was after, having a lot of conversations with all of the ARM chip vendors, ARM themselves, looking at what IP and core designs they had in their roadmap, et cetera, that came to the, sad realization that it's not quite there yet. So our ARM v8 specification just came out that summer. All of the chips out there were still 32-bit ARM v7. And so ARM v8 was still going to be around the corner, but even that first generation of them, I didn't think were going to be really competitive in the market against what, projecting for Intel and AMD on the x86 side. So it was really then at the beginning of 2014, 10 years ago, that said, okay, well, if ARM isn't going to be the solution, then what could we actually, build ourselves? It was extremely naive, bit hubris, but I think the general thought was, okay, with ARM v8, they're actually embracing a lot of the CISC elements of x86, and they're still not actually providing a real competitive advantage. And the real root of the idea, like end of 2013 or early 2014, was I have this Thiel fellowship. It's, I'm getting $50,000 a year, which is nothing in to live in the Bay Area. But I was okay living with, 5-6 other people. So basically what the Thiel fellowship really gave was that freedom to think a really crazy idea, like, why don't I make my own processor architecture? And actually take the time to explore that in a way that didn't feel like the immediate time pressure of I need to support myself beyond the fellowship.
Right. That makes a lot of sense. Additionally, at that time when you were looking at the ARM IP that was available, you're kind of saying that you have that freedom, so maybe this wasn't as much of a consideration, but was the cost of licensing ARM IP, did that come into play, or was it mostly just like the capabilities weren't there at that point?
It was really the capabilities. Thankfully, had some really great connections with folks at ARM, and they were trying to be, extremely supportive. They early on, but from the connections made at MIT, the folks that at ARM that wanted to go up to higher performance and capabilities, we're trying to be as helpful as possible. But as we've seen in this past decade, ARM's only actually got competitive in the past 3-4 years. So it really took time for all of that to evolve. And I should say that also evaluated other architectures, and I think a large part of the drive to think about designing new architecture from scratch was seeing that there were plenty of what I thought were good, interesting ideas. Be it a decade before that with MIT raw and Untitled era, and then later as I learned about multiflow 2 decades before, et cetera, that my thinking at the time, especially being in the Bay Area with the entrepreneurial vibe and a lot of people's thinking being around, there were plenty of good ideas in the past that failed for not because they were bad ideas, but it wasn't the right time. Being a big thing kind of lended credence and belief on my part that this could actually be the right time to do something new.
Absolutely. That's one of the things. So most of the research I did for our discussion today is from this talk you gave at Stanford, where you really go through what y'all build at Rex, essentially. And I'll link that in the show notes and would encourage folks to watch. But one of the things that I really appreciate, and we'll talk about some of these concepts here in a second, is the callbacks you do to talk about these designs that have maybe been used in the past, or concepts that have been used in the past. And in some cases are kind of like mocked, right? They're regarded as not working out, and you kind of go through it and debunk some of those. That's something I find really interesting, looking at even like the RISC versus CISC debate, right? Because that happened in the 70s and 80s and things like that, and then we seem to go the way of CISC architectures with x86, and then obviously, right, with what we're talking about with ARM and RISC-V and some of the stuff y'all were doing, obviously RISC has come back into vogue here. Actually, tomorrow I'm another kind of like behind the scenes. I'm recording with Robert Gardner, who designed the SPARC Instruction Set, and we're focusing on register windows and talking about like why they succeeded and why they didn't. So there's a lot of times the reason things didn't succeed is not that they just weren't good ideas, right? There was some other factor, and maybe we can use that kind of to jump into what y'all were starting to build there. So I think my main takeaway was like two big concepts from the architecture that y'all designed, and that was VLIW, so very long instruction word, and Scratchpad Memory were kind of like the two things that I took away from that talk. Do you want to maybe start with VLIW and talk about the history of that and why y'all chose to go with that architecture?
Yeah. So I think a big reason I gravitate towards the history is, other than my love of electronics as a kid, I was very bored in school in general, but the only class I was very actively involved in throughout my school, it was always history. And so I just loved learning about everything from ancient Egypt and Rome to World War II, and really getting an idea of the causes and effects, and how everything has branched out from over only a few thousand years of modern history. So
Right.
that always fascinated me. And then computer history, and how like the fact that really electronic, or if I expand a little bit, mechanical computers have a much shorter, less than 150, 200 year time frame, and the evolution there has been remarkable. And I just, me learning any of the technical details of things, it just becomes so much easier, and I think I make deeper connections, both from a just personal enjoyment standpoint, but also like being able to analyze things in, I think, a different way than others by actually learning the real historical line of things. Like if you understand why in general smart people made certain decisions that in retrospect people ridicule, if you actually look back and look at the context of how they came to that decision, it gives a lot more insight, and usually suggests that no, they weren't dumb. They actually made a pretty reasonable choice given their constraints and such. So but an interesting thing, just since brought up the RISC CISC wars in the 80s and beyond. A lot of people don't actually recognize that RISC was actually a thing before CISC was in the 60s, and it's kind of overlooked. But a lot of people, that are nerdy about this sort of thing would argue the CDC 6600 was the first RISC machine. So that was, Seymour Cray designed first, real supercomputer that had mass market adoption. And fundamentally, what is RISC? I would be, a lot of people, probably because it's the easy thing for more lay people to understand, just think, oh, well, you have a fewer set of instructions that you build out and, do pipelining and things like that. But fundamentally, it's a load store architecture. The fact that you're having to actually move all of your data into registers, and you're operating on registers, is a very different paradigm from, early CISC machines, going, System 360 onwards. And so, if we go back to what I think of as being the first real CISC war of going between, Control Data Corp, which Seymour left and formed Cray, but the first real RISC architectures there versus System 360, which Power, I would I actually haven't looked into like Power 10 recently exactly where they have compatibility breakoff, but a huge constraint on the Power architecture for a very long time was IBM's insistence on being able to have binary compatibility all the way back to like 1968.
Right.
I think they still have it on the Z machines, which isn't Power. Or yeah, there's other processing elements there, but yeah, the evolution of RISC to VLIW, a lot of people, and I would say the first true VLIW was the ELI, which was extremely long instruction, 512, which was Josh Fisher, which then led to Multiflow that I mentioned earlier. But a lot of people don't actually know about floating point systems, and they're supercomputers from the mid 70s that didn't call their thing VLIW at all, but has all of the key characteristics of, the name is misleading in saying, very long instruction word. Everyone just thinks, okay, that must be what defines a VLIW. But in the same way that I would say RISC is fundamentally that load store architecture, you're doing all of your operations on registers, and you're needing to move that in and out of whatever other parts of your memory before and after operating. The core thing with VLIW is this idea that you can actually be doing concurrent operations that is very distinct and different from just parallel operations, and that you can encode in such a way that your instruction stream and that very long instruction, all of the operations that are being given in that single word are things that you are making a guarantee with the system that the programmer or whatever is emitting that instruction word is making a guarantee that these things can all operate concurrently without hazards. So,
Yeah, absolutely.
And that was extremely powerful idea in for the mid 70s with FPS, and then in the supercomputer space. And then it was really, I would say, Multiflow that tried to take that to a much grander level and be actually saying that we're going to build a compiler that can do this for you, that it's not the programmer, a really brilliant person drawing things on paper, in the 70s with FPS and trying to manually schedule this, but that this can actually be a control flow graph, and you can algorithmically determine what things can be done in parallel. And that, frankly, has been the holy grail problem for 30, 40 years now as it relates to VLIW systems.
Absolutely. And, when you talk about different ways to get instruction level parallelism, the, what we're kind of talking about, and this is with RISC and CISC as well, perhaps, is do you do more work in the hardware, or do you push more complexity to the hardware, or do you push it into the compiler? And, the way computing systems have evolved have changed that trade-off. So some of the discussions, looking back at things in the 70s and 80s, assumptions about, for instance, you mentioned a human, writing a program. It's very different when you're comparing that to a compiler generating machine code. So that's, one of the things that I frequently see with some of the research from back in that time and then applying it today. That's just one vector where the trade-offs may have changed, throughout history. The architecture, the processor that you referenced in that talk that kind of gave VLIW a bad name was Itanium, which I'm sure a number of folks are familiar with. So with VLIW, we can potentially reduce the complexity of the processor, right? Because we're pushing more of that onto the compiler. Can you talk about why Itanium was not successful in doing that, or why it's maybe mocked today?
Yeah. Well, as I mentioned in that talk, and I'll stick to my stance here, I do not consider, this is trying to disown a not even my own child, but something that gets associated with the thing that I love.
Right.
But I do not consider Itanic to be a VLIW architecture. And my best evidence or thing I can point to support that is Intel's own marketing from the time, which they were very explicitly trying to say that it wasn't VLIW back then. They coined this EPIC name, so it's the explicitly parallel, instruction set computer. And I appreciate whoever in the marketing department at that time, was doing that. Um, and but even the technical reasoning for doing that was their belief that they could actually take the really powerful, amazing thing about VLIW of being able to have these explicitly encoded parallel or concurrent operations that could be done. And I would say they had a bit of, and I've heard different stories from different people involved at the time, but in general, I think everyone would agree that there were strong battles internally in the both Itanium team itself, but being heavily, heavily constrained and influenced by other parties within Intel that were really trying to heavily push the x86 Pentium continuation elements. And what I think the real downfall for Itanium in diverging from sort of the pure VLIW roots, which have ended up being successful in many other products that we'll talk about, but was them trying to still have support and some level of compatibility with x86 and all of the elements and kitchen sink pieces that were getting moved in from other parts of Intel and being bolted onto Itanium that kind of turned it into not being VLIW and I would say very much being epic and turning out to be an epic fail. I just, I guess expand a little bit on it. It's fundamentally comes down to what I was saying before, where VLIW is the programmer, the compiler, whatever is giving that instruction. It's its job to actually be saying that we know at this cycle that you're going to be having no control or data hazards with this data you're providing. And when you start to try to add a lot of advanced processor features like branching, or branch prediction, any sort of caching systems, and especially if you want to actually have some instruction compatibility with x86, which was a big and goal that Intel never actually even delivered on with Itanium. You add in so much requirements of non-deterministic features that guarantee can't be made. It's right. Impossible. Like if the delusion and the reason I think that the Itanium failure is so well known by people that aren't computer architects, but that they still associate as VLIW bad because of Itanium, don't realize that it wasn't that they just weren't able to make a sufficiently smart compiler. That was an impossible task. It's I would say probably not provable as impossible, like P is or is not equal to NP. I would say it's similarly non-determinable, but any rational person, I think, would be saying that P is not equal to NP. And if it was, then the whole world collapsed and none of us, nothing we say right. about it matters if it was. And so I would make a similar assertion that Itanium's mythical magical compiler was impossible due to all of the non-VLIW cruft and design directions that they tried to do it to make it a appealing product from Intel's internal perspective. And fundamentally, I think that those decisions were rooted in Intel didn't want to actually diverge from x86.
Right, absolutely. That's kind of a it once again kind of referencing back to like where you put the complexity. You have to make sure wherever you push the complexity that you give sufficient information to make the decisions in that place. And it sounds like in this case, right, the compiler authors or humans writing machine code or assembly, they didn't have sufficient information to reason about performance and maybe some of those hazards as well. So that makes a lot of sense. And then with
you're having to take a full pipeline, flush of 40 plus cycles at that time, if I remember correctly, you're going to have a really bad time. So right. I think the key thing to remember is like code worked on Itanium. You could run programs; they just performed horribly because those guarantees that correct level of abstraction and where the handoffs are in complexity were like, I think this is the other thing, and why I don't think a lot of the engineers and people associated with Itanium like to talk about and don't like to correct the record on a broader scale, is because so many people, and it becomes like within the broader computer science, culture, like a known failure beyond just in computer architects that people don't like give credit to the engineers. The engineers actually want to make a good product. They actually want to do, the right thing. They made a lot of good decisions, but when you have the wrong requirements going in and the wrong, request demands of a system, you're going to end up, not making the right thing.
Right, absolutely. Well, so in your Neo architecture that y'all designed at Rex, y'all took a different approach, and you talked about in that talk having hard real-time determinism. What was kind of the strategy? Are there any kind of like things you could point out specifically in the processor architecture that allowed you to be able to do that in contrast to something like Itanium?
Yeah, so probably the biggest element that stands out, but also vastly simplifies everything, is the fact that we went to a purely Scratchpad-based memory system. So in terms of what would normally be, L1, L2, caches and traditional processors, rather than having the TLBs and MMU and all of these extra pieces of logic, which take up a lot of area, a lot of power, a lot of design time and complexity, and add latency and such. Basically, think of, you've got your L1 cache, but we just rip out all of that, and you're just directly accessing that memory, the physical addresses for those pieces. So at the individual core level, it was, and I think a lot of how we talked about it to most people, just think of it as being a simple RISC core to start off with. In reality, it's VLIW, but VLIW got such a bad rap that it still meets the definition of RISC. And most people don't actually care how instructions are generated for it if they're not responsible for doing anything related to it. Right. But had a 64-bit ALU, IEEE 754 2008 compatible 64-bit floating point unit, and then 2 separate register files for each of those, and then the Scratchpad memories, which were divided into multiple banks. And really the VLIW, the instruction word that used to control these elements, enabled you to be doing an ALU op, a floating point op, as well as 2 load and store operations simultaneously, all in a single cycle. And at that basic core level, that sounds pretty simple. It's no more difficult than, and in a lot of ways a lot easier than programming computers pre-1985-ish with the proliferation of caches. Like you just directly access the memory system, and it happens that a single one of those cores had more main memory just embedded within that core than a lot of the early computers that probably a lot of people listening to this podcast grew up with in the early 80s, 90s. So but yeah, we expanded. So the core difference is that just having that direct access to memory drastically simplifies, and the benefit from on the software layer is because you have that exact deterministic operation for every single instruction you're doing, all of your memory accesses take a predetermined number of cycles, number of nanoseconds. When you're actually generating, when you have your compiler and the compiler is trying to generate a control flow graph for your program, it knows exactly when data is going to be where, and that there's not the potential that the hardware is actually going to be doing something in secret, and there's going to be a stall that needs to be inserted for God knows how many cycles.
Right, and when you were describing that, it kind of made me think it feels like a similar kind of like pushing the complexity, or maybe even you could say pushing the capability onto the compiler to, not just in the instruction and control process, but also in the memory system now, which is kind of like interesting to like lean fully into that kind of model.
Yeah. Yeah. And so, and it's not like no one was doing that between Itanium and us. Like there are plenty of VLIW architectures that had great success, primarily in the signal processing world. And so, uh, between 2000 and at this point 2014, 2015 for REX, there were like basically every single cell phone. If you think about the number of devices there, maybe by 2015, I think it would be believable that there were more VLIW processor cores out in the world than x86 processor cores, because it would be in every single baseband for your cell phone. It would be in every DSP that's doing any ADC DAC work with anything that has microphone connected to it. So the VLIW, what a lot of people don't realize is VLIW won in a very silent way in application segments where you needed that determinism. Like in most of those DSP applications, it was a requirement going into the design of that processor and the overall product that those processors would be going into, to have some like hard guarantees on timing. And the easiest thing for those designers to do was ensure that the hardware behaved exactly as designed, and not to have these elements that were originally designed to make general programmers' lives easier. Like the reason that hardware managed caching took over was back in the late 80s through 90s, processor architects were getting free transistors every 2 years. And so if you just keep getting free transistors and you almost don't know what to do with it, you're going to start adding complexity to your design in order to make what is thought of as the your end customers, the people that actually need to program and utilize these machines, make their lives easier, allow them to address a virtual memory space and not have to understand all of the increasing complexity that's being introduced. And I think fundamentally the big our thesis for REX was we wanted to do much grander programs, applications than what DSPs were restricted to, and we were targeting, a higher level of performance, et cetera. And our belief, and I think, we did prove out on this, is you can have a sufficiently advanced compiler to be able to do that sort of scheduling, as long as you make those guarantees, and if you're willing to actually spend the time with compilations. Like our compiler wasn't fast. It was developed for off of LLVM. So I think like the big advancements that only really came in the early 2010s was, sufficiently advanced open source compilers were there. So the LLVM project was, the biggest advancement to actually allow architecture independence, and Apple's investment of actually making that open is like one of the best saving graces for the entire industry of the past decade. Like I don't think we can thank Apple enough, and Chris Latner and everyone involved in that project, for not only doing a good job and making it possible for Apple to do the portability that they wanted for Mac, going from PowerPC to x86, and then they wanted to also enable those developers to develop on an x86 Mac, but for a ARM iPhone, and then eventually them now moving fully to Apple Silicon based on ARM. Like they could have kept all of that closed into themselves, but they realized that was also a really big problem for Google and Microsoft, and actually making that a whole community was one of the greatest developments of like the past 10, 15 years, in my opinion. Directly enabled us with REX to be able to start off with a really advanced, SSA form of the static intermediary representation of LLVM IR, and then be able to do our specific optimizations and that control graph work to be able to emit, efficient performance assembly for the architecture. And even though that compilation time took longer than if we just went with a RISC and had all of that complexity in the hardware, like compared to, the late 80s or early 90s or, 2000 with Itanium, just base computers, just the desktop computers that we're doing compilation jobs on were so much faster. So, I think VLIW to actually have VLIW be broadly successful and usable for larger applications than what they in this embedded spaces where they were successful really needed you to be willing to spend a lot more horsepower on that compilation stage, and just the natural evolution of computing performance enabled that to actually be practical.
Absolutely. You talked about last time when we chatted a few months ago about the kind of like software side of things sometimes being the hardest part of developing new hardware. So you mentioned there, that y'all leverage LLVM, which was obviously hugely advantageous. What other kind of obviously there's porting of operating systems and things like that, but what were kind of like top of mind for y'all when tackling things other than the compiler that you thought were necessary to enable the Neo architecture to get adoption?
Yeah, so our real focus on the compiler side was getting base LLVM and Clang working. So Clang is the C and C++ front end for LLVM. At a high level, LLVM is kind of broken into three pieces. There's LLVM front ends for basically any high level language you can think of. Those front ends then actually output this LLVM IR, the intermediary representation, which is a static single assignment, representation of the program. But basically, there's no mapping to actual registers or anything that is like hardware specific at all. But you have a control flow graph, and you can like get a lot of intelligible and do a lot of optimizations like just on that SSA form. And then finally, there's the backend that takes in that LLVM IR and actually generates assembly and machine code for the target architecture. So LLVM being standing on the shoulders of giants there for those the front end and a lot of the IR optimizations, but we had to build a custom backend. Thankfully, like there already was a pretty good VLIW backend that Qualcomm released for their Hexagon DSP. And if I remember correctly, it wasn't actually mainline LLVM yet at that time. They had their own branch. Then I would say we more learned from that in developing our own backend than like there are plenty of differences with Hexagon. But that was the biggest lift. But even once you have a compiler, even if you've got a C front end, that's kind of useless if you don't have like a libc that is actually targeted for your architecture. So my co-founder Paul Sebexon was really the software brains behind Rex and doing all of that work basically single-handedly. So I think it also, I didn't really talk about the founding of Rex or anything, but I am very, very proud of what we did with basically 4 employees, and going from raising our seed round in 2015 to taping out in less than a year from raising money, basically 6 months from actually getting started on real RTL that ended up in the final thing. So having all of that, and even just getting to that early level of a C compiler that can actually take basic C, was a really great starting point. But where I think a lot of the our plans were not in that reasonable time to have an operating system running on there, but actually having a good CUDA, or sorry, not CUDA, thinking of modern things now. But having a good BLAS library, so the basic linear algebra subroutines, be able to have those optimized for our design. Like the first benchmarks, like what we showed at that Stanford talk, was our gem kernel and an FFT. So getting those to actually compile and run through was accomplishment, but obviously the industry as a whole has much higher demands of supporting much larger packages and libraries than what we could tackle with our team size.
With the kind of like accelerated timeline you had because of funding, but then also the time it takes to get a chip taped out and get it fabricated and that sort of thing, you obviously had to be working on software in parallel with the hardware. You talked a little bit about this in that Stanford talk as well, but what kind of strategies did y'all use? Did y'all have simulators that y'all built for the architecture? What was kind of your process there as a team?
Yeah, in large part because we didn't have much time just from a base burn rate situation, and because we only raised $2 million, which sounded like a lot when I was 18, and but it doesn't last long, and we couldn't afford any fancy simulation or emulation tools, and so our software development and all of the verification that we did on the design, and basically we started RTL and hired our head of engineering in November of 2015. Between then and when we taped out in June of 2016, was all done with Verilator, which is an open source project. I should clarify that there was waveform simulation done just like for individual blocks. That was done just with Incisive, the cadence simulation tool. But anything that was like a full core and greater was done using Verilator, which a lot of people told us was very crazy. Using an open source tool to be the thing that we're trusting to actually tape out a test chip on, and we did have to make a lot of modifications to increase performance with Verilator to get to the level we wanted. We started off with very crazy ambition of being able to do a full core level synthesis. So going from RTL to having a net list, every single day. And we did get there basically by January of 2016. So we were doing very rapid iterations on our cores, and at least weekly having full top level synthesized, and having our golden model was that RTL that was being synthesized, and taking that exact RTL, running it through Verilator to generate that C++ simulator of that RTL, and being able to actually then use Verilator to generate waveforms to compare with waveforms of individual blocks. And so that whole development flow was completely foreign to every single person we talked to in the industry. But if we didn't do that, there was no way we were going to be able to build a chip on that schedule. And it was it's funny now, having spent the past 6-ish months working on some new hardware, haven't been able to replicate that level of what we're doing now is a bit more complex and everything, but
right.
It's crazy to think back that we got that done purely out of necessity, and it worked
right.
without major problems.
Absolutely. Yeah, I've used Verilator before myself, and it's excellent. And another thing that's, I think, in the last maybe decade, so
we had a lot of problems back in 2015 that have been fixed since that.
I'd imagine so. One of the things that, so I've mostly worked on FPGAs, and after that, it's similar process of going through synthesis and netlist generation and that sort of thing. But then you eventually generate your bit stream to load onto the FPGA. And one of the things that's been really nice, being an individual who's doing much less than y'all were as a 4-person team, but is the open source tooling around synthesis and that sort of thing, which has really in the last decade, maybe even 5 years, you could say, grown up quite a lot. But everyone I talk to who works hands-on in the industry still indicates that there's like a pretty significant gap between what's available open source and the proprietary tools.
Yeah, and yeah, I have played around with the open source synthesis tools, and it's I guess I feel like I'm spoiled brat in saying that. Yeah, I just can't touch it. Verilator still, I think, is for doing the specific things it does really well, which is enabling you to have very, very fast simulation. Like we were doing full chip simulation based on taking from RTL at like 1.25 megahertz. And then this was simulating the full 16-core chip on 2015 era low cost Xeons. So
right.
Like our incisive simulations were running in the hundreds of kilohertz. So way less than that. I think 10. It was somewhere in the order of 10 to 50 kilohertz.
Wow.
So being able to actually do, and I think that was like single core, like we couldn't even, I don't think we actually did anything larger than a single core with incisive. So yeah, it's Verilator enabled us to do, constrained random test generation and actually doing, nightly regressions and everything that, sure, we could have bought a very expensive tool from Cadence or someone else to do that. But I'm pretty sure we actually ended up with something that worked better for us, just with that free open source tooling. And then like when it comes to Yosis and everything today, I think in large part because there's not really a practical way to use all open source tooling to get to building a anywhere close to leading edge chip. Like I know there's the open I'm forgetting the name of it, the Google sponsored project for doing shuttle runs with
OpenMPW.
Yeah. And so I think that's great for students, and I'm glad that something like that exists. But I guess I've gotten spoiled there, where I'm never going to make a chip. I already made a chip at 28 nanometer. I need to be going smaller and smaller to take out. So
right.
So, but yeah, that's. And finally, just on the FPGA note, we actually didn't start doing FPGA simulation, test of our chip until after we taped out. So
really?
We were so focused on getting the chip working. We actually did buy a pretty high-end ultra-scale, Xilinx ultra-scale FPGA to do simulation with. And we tried doing some things before tape out, and it was taking too much time and we weren't making progress with it. So we just said, hold off on it. And we didn't actually start using the FPGA for doing some physical testing of connecting to the development boards that we were designing before we got the chips back. We wanted to test some of okay, can we have this on the FPGA and actually connect, the microcontroller developer board that was going to be put onto our chip? Can we take that evaluation kit we got from ST Micro and connect that to the FPGA and actually have that communication work? And then we found bugs in our design post tape out on that FPGA, which was sad, but we because we had that time of knowing those bugs existed, we figured out ways to get around them by the time the real chips came back.
Right. And obviously, the company kind of wound down a little bit after y'all got the chips fabricated. I do have to ask, where are the chips today? Do you still have them on hand? Have any been, what are the interesting use cases that they've been used for so far?
They make nice display pieces.
Yeah.
They're not very good heat generators. That's some of
Right.
cold nights. I'm like, I have 181 of these chips, in my closet. It would be nice if we made it too power efficient, so it's just
Yeah.
can't use the space heater. Um, yeah. The long story short on that is you know 2017. You know, I think we officially ran out of money 2 or 3 months after that Stanford talk. So
Mhm.
April, May of 2017. A lot of reasons for that, which we could go into, um, but yeah, the I think key thing from like what can the chips do? We had amazing floating point performance and efficiency for what we had built, this low dinky 16 core test chip. That like measured, validated, double precision floating point performance per watt on 28 nanometer was better. It's basically equivalent to NVIDIA A100 on
Mm.
what, 7 on TSMC 7. So like we were able to demonstrate that worked. I would also say, even though the software was really early, it had the components there to show that with more people, more time, the software stack can function. The core problem with the test chip was we, in the early fundraising we did, and kind of our belief primarily as technologists when starting the company, was that we needed to build a chip. That was what we had to do to show potential customers, investors, et cetera, that we're serious. And a large
Right.
part of that is also we were both really young. 18. My co-founder was 20, and so we kind of had blinders on of we just need to get this chip, and once we have the chip, that will be what unlocks us to get to the next step. And well, I should say chip plus the basic software tools around there, and then all of these investors that to our faces had told us that they didn't believe we could actually make a chip when they decided not to invest in us. Then they would come around once we demonstrated we could do that. And it wasn't until after we had the chip and we were very proud in demonstrating that it became very clear that, oh, this thing we built greatly demonstrates the technical potential, but it doesn't
Hmm.
actually demonstrate like it was a little 12 square millimeter test chip. It was
Right.
never designed to actually do the thing that the 100 square millimeter version would actually be useful for. So
Right.
um, that focus on just getting to have silicon and proving that would have probably actually worked out fine if we had raised 3 million or 5 million, if we
Mm.
had some more buffer from when we had, because you know we were running on fumes by February of 2017 when giving that talk. Um, uh, Basically, by the time when we started talking to investors and customers, and they realized our cash situation, everything turned into acquisition
Mm.
conversations. Um,
Right.
so it still worked out in some ways, but um, the other big problem, you know, we gave up a very very large amount of the company in our seed round.
Mm.
So that for that $2 million initial investment, it was on a 3 million pre-money valuation.
Mm.
So we gave up 40% of the company at the very beginning, and
Right.
we actually did have two different investment offers that would have recapped the company, but uh, turns out investors that have the ability to block new investment coming in and such don't like having themselves diluted a large
Right.
amount. So uh, yeah, I think we kind of almost like signed our death certificate from the very beginning, where we didn't raise enough to ensure that we could get the chip and still have enough viability that we could have more extended conversations and make that real proof point with the technology demonstrator that we had.
Hmm.
Um, And then secondly, we just gave up way too much of the company to actually make an appealing investment to anyone else. And like when it came to the acquisition talks, when folks looked at the cap table and saw that we owned such a small part of our company, it's like, why would they want to pay, you know, the investors and have them get all of the benefits when after that deal is over, like the primary reason that they buy, they do an
Right.
acquihire is to, get the people and, some value of technology. They frankly don't care and would like the investors to get as little as possible. So
Right.
that was a very tricky situation.
Yeah, yeah, absolutely. Well, so you went and did a few different things after that. We're gonna fast forward through those. Maybe in a future episode we'll have you back to talk about some of those. But you recently started a new company and just kind of came out of stealth, as we mentioned at the beginning of the show. Do you want to talk a little bit about what y'all are doing at Positron and maybe also some of your recent announcements?
Yeah. So back April of 2023, started a new company, Positron AI, developing new hardware for accelerating machine learning models in the general sense, but like 95% of our focus is on transformers and specifically like the large language model and large multimodal network types. And so we haven't announced too much. We did exhibit at the NeurIPS conference last month and sort of had a soft launch. But we're going to be making some more like real product and shipping product announcements this spring. But at a high level, we're what we did show at working demo of our PCIe card based accelerators, having about a 5x performance per dollar advantage over NVIDIA H100 for Llama inference. So and some of the upcoming announcements are going to be significantly greater than that for some of the newer exciting model types that are out there. So our core belief is that what are considered large language models today are going to be puny in the not so
Right.
distant future, and we're making a very strong bet on having very large amounts of memory capacity and having the right balance of memory bandwidth to compute. And like the core thesis of why we started Positron was that the sort of first generation of AI accelerator chips that all the companies that were founded basically 2016 17 till 2020 at least, and even a number after that, really based their designs on the ratio of compute to memory that existed for convolutional neural networks and other neural
Mm-hmm.
network architectures, where you could throw as many flops as you want, and it improves your actual realized performance. And fundamentally, what's different with transformer models, especially on the inference side, if you want to have good throughput and latency for that model, it's a vastly different ratio required for memory bandwidth and memory capacity. And so, we're targeting, like with this first generation product, having, an order of magnitude greater memory capacity than what is possible on NVIDIA GPUs, be it today or in their upcoming product releases. And having a much higher ratio of memory bandwidth to the actual flops.
Is the what does the compute or the software integration look like for a processor that's specifically focused on accelerating inference? Obviously, NVIDIA has CUDA. There's a couple other. I think it's AMD that has ROC. There's a couple different models there. Does y'all's architecture fit into some of those software stacks, or are y'all developing your own?
So the big thing, and what got a lot of interest and people looking at us very differently from, I would say, all of the other people trying to compete with NVIDIA,
Right.
is the fact that our software strategy is actually we don't have a compiler, or there's no compiler that any user of our stuff would ever know about or care. And so really how this first generation product is the operating model for users is we have we ingest directly the trained model file for these transformer models. So, .pt is the PyTorch output file that when you do training, primarily on NVIDIA GPUs, that's the output. You can, there's safe tensors and a couple other formats, but taking that trained model file, that is directly what we ingest and put on the device. And so there is no porting, there's no, the story that AMD and Intel and many others have tried to tell, and to varying levels of success of actually being able to do anything close to it in reality, is that them saying, oh, well, we support PyTorch, or we support TensorFlow, or we have a process where you can go through 16 steps to convert your PyTorch model to Onyx, and oh, actually, we don't have that offset support, and Onyx is always 6 to 12 months out of date on new features, being supported, or they just decide that they're never going to support that particular op. Rather than dealing with all of that has been the bane of the existence of anyone trying to move off of NVIDIA. We're actually being able to take directly your config.json for your Hugging Face Transformers compatible model, and take that model file and directly load that onto the device, so that there's zero our compatibility process is, well, if you trained it on presumably in NVIDIA, really, if you trained it on anything, and that it's a model architecture supported by Hugging Face Transformers, we're able to ingest that directly.
Wow, that's definitely a huge benefit there. Was the I could also imagine not only is that really nice from an integration perspective, but if you are a startup, a smaller company, removing the need to build all of that software support is also nice from an organizational perspective.
Yeah, it's drastically simpler for the customer users, which is the number one thing, but anything that can also make our lives easier. And we're very clear in our stated mission and goals that if you're using some 3D UNet piece, technically our hardware can support it. Technically we could, and actually in one case, like, we've gotten a very simple version of that running and going through this, but at least in the foreseeable future, we're not going to be offering that to customers as an option. We want this to be the simplest process for us to be able to get a product out to market, and people actually having a viable alternative to NVIDIA. And I'm knocking on wood a little bit. We're approaching 1 year from the company being founded, but it was our goal from the beginning that we would actually have real product in customers' hands a year from delivery, and it's looking like we're going to hit that. So it's another key lesson from Rex and other experiences that I've had since then is identifying what is it that the customer is actually craving for. What is their the real pain point and desire that they're making their decision on, and just narrowly focusing on that, and keeping your hand on the pulse of the customer throughout the entire development process. Be it myself with Rex, and I think the failure point for a lot of companies, be it new processors or otherwise, I think probably one of the main reasons companies fail is that they're too focused internally building and building something that they themselves want, rather than really deeply understanding and being obsessed with making something that the customer wants. And if even there is a line, and you have to use a lot of judgment and it's a process to it, but the customer is not always right, but they're usually more right than you are in making decisions of what is going to cause them to part with their hard-earned dollars for your thing. So you obviously don't want to just build a faster horse when you could have made a car, but there's a balance which I'm still trying to find, and I think all entrepreneurs need to work on that. But it's definitely a really hard problem to, and an exciting one. It's the fundamentals of how do you actually build a successful business.
Right. On that kind of set of customers that are, interested in a processor that's going to accelerate inference, what are kind of those key pain points or the key things you think people are willing to switch for? I mean, some that come to mind based on, what you've described your product is the interface feels like it's really important, right? And y'all having a really simple, maybe even you might say high level interface to your architecture could go a long way. I know availability is also just a big thing today. In terms of other aspects of y'all's product, what are things that you've heard from customers and then tried to incorporate in as key tenets?
Yeah, I think the fundamentally, I think the vast majority of purchasing decisions, if you assume that it's functional for the application that they care about and that they can use it in whatever method that they desire, the next step of that purchasing decision, where things boil down to, is the performance per dollar. So it's can I actually is this going to be a net savings? And when going in against an incumbent, you need to have, it can't be something that's 10%, 20% better. It needs to be, ideally everyone says an order of magnitude. So
Right.
Somewhere between those two extremes is a great point. And the nice thing about this particular market and how we're trying to address this is, what we're selling is actually not the chips. We're selling an appliance, a full system. Mm-hmm. And we're really treating that as being like a black box for LLM inference. So, you can use either publicly available model. We're aiming to work with partners that have their own closed source proprietary models that would be able to be run on our hardware and accessible to others, or you could bring your own model. But from that point on, it's no different than the interaction method with any NVIDIA system. Where we have an OpenAI compatible API front end. We've built a load balancing system that can actually is hardware agnostic. So requests can hit that load balancer and be distributed to a Positron box, to an NVIDIA box, to an AMD box, as long as that API interface is the same as what those customers are used to. And most of the industry has kind of gravitated to the non-officially defined spec by OpenAI, but the one that they created for their own services. And if you support that, there's really no change from that user's perspective. They're simply sending tokens in as a prompt, and they're getting tokens back as a response. And so that's token in, token out model is really one of the biggest enablers to making this easy from a actual usage and adoption standpoint. Once you get beyond that point of, okay, is the model that I want to actually run capable of being run on this hardware?
Absolutely. Is the obviously things are moving at a pretty rapid pace in this area of the software and hardware industry. Are there any kind of like concerns or future proofing y'all do around building this hardware that adheres to that interface, to ensure that your product will be viable for an extended period of time?
Yeah, a key thing, where even though we call what we've built principally a transformer accelerator, fundamentally it's a linear algebra accelerator that has a very clever method and connections both for the memory system and for scalable networking of many of these things put together. So from the perspective of new model advancements, just in the past few months, there's been actual first, I would say, real viable competitors to transformers in the case of state-space models. So there's Hyena and there's Mamba being two things that caught a lot of attention last month at NeurIPS. And while it's still, I think, too early to tell if they are going to actually scale out to wider usage in their current states, the fact that we're fundamentally a linear algebra accelerator, like the hardware maps just as well to those different ways of solving similar problems than how transformer, multi-headed attention and transformers do it. So we feel really good about having that flexibility of changing as model architectures do. And I think the biggest advantage we have the thing that I don't think that the other hardware providers are really equipped for right now is being able to scale to larger model sizes, especially with things like, I'm not saying dense models as a necessity, like the whole emergence of mixture of experts with GPT-4, Bard, and now the Gemini version of Bard, and now like Mixtral being in the open source space, having this method of having many experts with only a small number of them being used for every given token actually increases the total amount of memory you need to hold the entire model.
Right.
And so that's like perfect for this architecture we've designed, where we can support having current things are capping out at like 8 experts. I'd be happy if things move to 32, 64 or more experts, because we actually have the memory that can hold that, and we can do that affordably. I think that even like the next generations and all of the new AI accelerators and things that are heavily embracing HBM as a memory technology are sort of going in the wrong direction. Yeah, HBM is great from a bandwidth perspective. It's in the name, but you're going to be paying at least 4 times more per gigabyte, and you have hard caps on how much memory can actually be supported per HBM stack, and how many stacks you can actually put onto a CoWoS package. And so we're embracing commodity memory as for our scaling story, which is what's really giving us that massive amount of capacity, and having the right balance of bandwidth to compute.
Absolutely. That makes a ton of sense. Well, Thomas, I know we're getting close to the end of the time we allocated here, and I don't want to take up too much of your time, but I do hope to have you on again in the future as y'all roll out some new products. What are some ways that myself and others can keep up with you and Positron as y'all continue to roll stuff out?
Yeah. So I would say the best ways right now are on Twitter, X. There's my personal TR Sohmers account, and Positron, I think it's _AI, but you can find that from my X account at least. And then our website's positron.ai.
Awesome. Well, we'll make sure to link those in the show notes as well. But it sounds like there's a lot of really exciting stuff coming up. So definitely we'll keep an eye on that. And thank you again for joining for one of the early episodes of this show. I'm very appreciative of the folks who are willing to jump on for an interview before they've heard any of the other ones. But I'm sure folks will get a lot out of this one. So really appreciate you stopping by.
All right. Well, thank you, Dan.
Absolutely.